Okay. Uh, so now that we have talked about, about diffraction, the diffraction grating and what is diffraction, in this particular talk, we are going to talk about the other kinds of problems that happens trying to image something. So this comes under the category of optical aberrations. So the optical aberrations are basically, deviations from the known optics. These are basically from the idealized conditions of Gaussian optics. So these are also called paraxial descriptions. Now there are two major classifications we can think of in optical aberrations. First one are the monochromatic aberrations. Under this, two things that we are going to discuss today will be spherical aberration and astigmatism. And there are other kinds of monochromatic aberrations as well. Okay? So what these aberrations actually do is they make the image that you are actually filming, makes the image very unclear. And in some cases, the image is also distorted. So it is generally good practice, therefore, to close the aperture of a lens by using one or two f-stops and to use a lens with its designed magnification range. So usage of lens becomes an important parameter in this particular exercise. But the main things are that when you talk about chromatic aberrations, these you also know from your lens formula, the prescription glasses that we wear. There is also another type of aberration which is called chromatic aberration. It comes due to the color, okay, the color that is contained in the light. So basically, we are going to talk about these three aberrations, and these are basically, remember, deviations from the idealized condition of Gaussian optics, which we know a little bit already. So when we talk about spherical aberration, let's look at this particular plot, this particular figure in details. This is a simple lens. So the rays which are going towards the center of the lens, okay, and the rays which are coming from the edge of the lens, which are basically called the peripheral rays, okay, they are basically focused at two different points. All right. So the lens is made of spherical surfaces, and the rays, therefore, which are parallel to the optical axis initially, but at some distances from the optical axis is the central line, they fail to converge, therefore, or they fail to focus at the same point, or the lenses are unable to focus it in the same point. As a result of that, you get what is called spherical aberration. So take a look at it here that, for example, these are the paraxial rays which are focused, say, somewhere around 2, okay, this point 2. And then there are certain peripheral rays which are focused at a point 1. Okay, so the distance between, and there are certain rays, okay, which, are go away from after focusing, and they diverge by the time they reach the point 2. Okay, so if we now consider this particular arrangement, now the ray which is farthest away from the optical axis, the furthest peripheral ray, that is going to have a certain distance from the optical axis at this paraxial focus point 3, and this is called transverse spherical aberration. This is the transverse spherical aberration. And the paraxial focus 3 that you see over here, and the distance from that and the first converging point, which is here, which is given as 1, this is called longitudinal spherical aberration. So the lenses with spherical surfaces, the rays which are parallel to the optical axis but at different distances, they fail to converge at the same point. As a result of that, they give rise to this aberration. All right. All right. So as we can see, what we did was that this is spherical aberration. So if you look at it in this particular picture, this will be even clear. This occurs due to the dependence of focal length, aperture for the non-paraxial rays, which are basically rays which are away from the optical axis, which are not close to the optical axis. As you can see, rays converge here and those rays converge there. Okay, so this is what we call the longitudinal spherical aberration. The longitudinal spherical aberration is this, which is LSA over here. As you can see, from this point to this point. Okay, so this is where the peripheral rays are actually meeting on the axis, and this is the far axis. Okay, so you can see that this is basically the LSA, is the envelope of the refracted rays. And then, of course, there is transverse spherical aberration as well, which is from the optical axis, from F1, basically, how far this particular ray is actually deviated. Okay, so this particular distance that is called the TSA. So the incident ray will undergo minimum deviation when it makes more or less the same angle as does the emerging ray. Okay, simply turning a lens around can markedly reduce the spherical aberration. Okay, the incident ray will undergo minimum deviation when it makes more or less the same angle as it does the emerging ray does. Okay, so this is spherical aberration. In other words, it is nothing but the inability of the lens to focus at the same point the non-axis or off-axis rays, which are non-paraxial rays, essentially. So astigmatism arises when an object lies at an appreciable distance from the optical axis. So, for example, here is the object point. It is not lying on the optical axis. It lies at an appreciable distance away from the optical axis. So the configuration of an oblique parallel ray bundle will be very different in the meridional and in the sagittal planes. As a result, the focal lengths in these planes will be different as well. So this is the thing that happens. This is the object which is away from the, optical axis. And these are the rays in the meridional plane, and this is the plane in the rays in the sagittal plane. So, so the configuration for an oblique parallel ray bundle will be different in this plane versus this plane. Okay, as a result, the focal lengths in these planes will also be different, which gives rise to astigmatism. This is very common when you are doing your prescription glasses. This is something that you are well aware of this. Okay, so if you look at this is your meridional plane that you see over here, and this is your sagittal plane. All right, so this is your sagittal plane, this is your meridional. All right, so it is well marked over here, and this is the object point away from the optical axis, right? And this is the primary image, and this is the secondary image, and this is the circle of least confusion. So all this leads to image blurring, essentially. So the fuzziness of the images comes from this. So you can see, so it's a very clear idea that sagittal plane and meridional plane will have focal lengths which will be different because of astigmatism. All right. So this is what it is, and this should be something that you know already, right? So next comes what we call the chromatic aberrations. Now, chromatic aberrations arises due to the dependence of refractive index on wavelength. Okay, in this particular equation, that means different wavelengths of light are focused at different distances from. If you look at this particular picture, you see that this is a singleton ray, one single ray. Not a monochromatic ray, so it comes and hits the lens. Now this is blue and this is red, so they are focused at different points of the optical axis. Okay, so for example, blue is focused here, the red is focused there. Okay, so there is a difference in which the different lights are focused at different points on the optical axis, done in both in the vertical as well as in the horizontal direction. So this, if you look at this is axial chromatic aberration. So this is axial because this is how the blue focal point of blue and the focal point of red are different. As a result of that, you get an aberration right over here. Okay, you also get what we call lateral chromatic aberration, is the blue and the red, the distance. Okay, and so this is the blue, and this is also, you can see that this is the red. So it is this difference. The red converges somewhere there, okay, and the blue converges here. So it is the difference between the two convergent points, okay, between red and blue, which actually gives rise to LCA, which is lateral chromatic aberration. Okay, so this is how the chromatic aberration part actually works. So you have both lateral, like spherical aberration, you have both lateral as well as axial chromatic aberration. And remember, in the case of spherical aberration, it had longitudinal and transverse aberration, right? So that is what it is. So that is what we are very clear about. All right. So this is the chromatic aberration. So apart from this, of course, now you have some visualization equipments like camera, lens systems, etc. So we are still in that visualization part before we go to the light propagation and scattering part. The cameras, if you look at high-speed cameras, they are typically of CMOS sensors, 1280 into 800 pixels, gives rise to a 28 micron pixel size, okay, and there is something around about 36 mm by 22.4 mm. It's 12-bit depth, okay, and usually it is heat pipe cooled, and there can be thermoelectric cooling as well. That can actually happen. So this is the two competing companies, Photon and Vision Research's Phantom. So you can see that the camera pixels and the corresponding framing rate at full resolution. So this is, for example, gives about 22,500. And as you go on reducing the pixel, as you go on reducing the area, you can image, for example, at 512 by 512, you can get almost 70,000 frames per second. Remember, your normal cinema is somewhere around 60 hertz or maybe 30 hertz. So this frames per second is quite a lot. And they are cooled. They are actively cooled cameras as well. Okay. The high-speed cameras, there are different makes. IDT makes one, then NAC, then Phantom, then Photon, and then Shimadzu. And these are the different models. You can see the latest models as of 26. This has changed quite a bit. The IDT has, for example, a 600 by 1200 frame resolution with an FPS of about 8,000 frames per second, and the memory is about 2 GB. This is the on-chip memory. This costs you about 80,000 euros. Expensive. The Phantom can go up to about 7,500. This memory can be changed, and this also cost about 56,000. Then Photon SA-X2 is about 1 megapixel. This is like rectangular, so this can go up to 13.5 thousand frames per second. This is again something which is a function of memory chip can be changed, and about $70,000, 70,000 euros. You can see that there are, and Shimadzu, which is HPV2, this has got a very low pixel, but the framing rate is 1,000,000, and the memory it can hold up to only 100 frames. Price more than 150k euros. So this is a very small pixel resolution, but it can take 1,000,000 frames. So this is appropriate for very high speed images or high speed events, which last for a very small duration. That's why in memory it can hold up to 100 frames at 1,000,000 frames per second at that kind of a resolution. So this is a particular feature of Shimadzu. No other camera can actually go up to that. See, all these cameras, even at reduced resolution, like I showed over here, they can go up to very high framing rates, but not 1,000,000 frames per second, right? There are high resolution cameras as well. So for example, PCO 4000 is about 4 megapixels. So 4000 by 2600 pixels. The FPS is rather low, 5. It takes images at 5 frames per second. IDS, for example, it has a 2.5 megapixel. FPS is on 12.5 FPS. Then Edge 5, this is a good one. So this actually has 2.5 megapixel resolution, and the FPS is about 7500 with an on-chip memory of about 32 GB. This can change. This can change quite a bit, and they're all very costly. This is 56,000 euros. So you can see all these cameras are very expensive, and but they are capable of very high framing rate, and they incorporate most of these optics, and they correct for spherical and chromatic aberrations and all those things. The lenses also comes with the camera with as per your requirement, basically. So the signal to noise ratio, if you look at it, this comes from Tropia's paper on and Christian Kahler's paper on comparison of CMOS and intensified cameras. So this you can see the PCO SensiCam, for example, it has got a resolution of 1 megapixel, 1.2 megapixel, 8 fps. Okay, and this is the interframe time between the two frames that you can take the next one. So these are all different types of cameras, and this is the black line is the SensiCam. So you that the signal to noise ratio that you have over here, and that is what has been plotted. Yes, you can see that this is the kind of features you get. So the other cameras are all plotted over here. Nantec Dynamics, high nanosense, 100 features. These are all different types of cameras that are all being plotted. Okay. So this is the kind of signal, and here in some cases, even at low signal, you get very improved signal ratio. Get high level of signal to ratio even at very low signals. That means you can recover very mild signals as well. That means even if the image, even if the illumination is poor or the intensity is poor, you can do that. Okay, so sense is very, very good at this very low signal values. And at high signals, of course, all the cameras show improved signal to noise ratios. Okay, but it is at low end. If you see, then you can see SensiCam over here does a very good job in ensuring that you have a very high signal or an acceptable signal to noise ratio. In other cases, the noise becomes very acute, and that is what happens. The signal is actually very low. So these are things that one needs to consider when one does cameras. It's not just about framing rate. It is not just about the pixel size. It is not just about the interframe distance, interframe time, but it is also about the signal to noise ratios. So these are actually long distance microscopes. So for example, there are many companies which makes it. Infinity K2SC is one thing. So these are basically working distance, field of view, and magnification. That is this we are talking about transverse magnification all the time. So as you can see that so these long distance microscopes, basically you can image from a long distance. It acts like a microscope essentially, but from a long distance. Microscope, you really need to bring the objective very close to your body. Okay, so that is what it does, and this is mainly used for measurements in harsh environment. You cannot get too close to your measurement window, but you want to measure a very small region. Therefore, the magnification becomes. So that is what you need to do. So there is near, mid, far. All these things are actually given. Okay, there are also telecentric lenses. The telecentric lenses are used in which you want to make the objects appear to be of the same size independent of their location in space. So what it does is basically it removes the parallax or the perspective error. And the simplest way to make a lens telecentric is to put an aperture stop at one of the lens's focal points, basically. So this is a conventional lens. Here you get the image. What happens is that the images may not be of the same size, okay, for a normal conventional lens, but telecentric lenses are used to make the objects appear exactly to be of the same size, independent of where they are located in space. So if you have two objects, which is one behind the other, for example, a conventional lens, they will appear of different sizes. But in the case of telecentric lens, that is not the case. So for example, this is sensor site telecentric lens. So in the central size of the telecentric lens, what you have is that you have this object. You basically have this particular image that is formed. This is object size telecentric lens, which does things in a slightly different way, and this is both sides telecentric lens. Okay, so these are the different telecentric lenses that are available. Many of these materials are available on the internet. You feel free to read about all of them. So that is what the telecentric lenses actually do. Okay, so it's basically to make the objects appear to be of the same size. Now, we talk a little bit about the laser sheet optics. Now, the laser sheet optics are regularly used to illuminate a given plane in a flow field, though the laser sheets actually have a finite thickness. Now, this is routinely used in measurements like particle image velocimetry. For micro PIV, of course, it is more of a volumetric illumination, as we will see. So, what happens is that in these cases, the lenses with negative focal lengths, which is basically the concave lenses, or a cylindrical lens, can be used to create this laser sheet. So this is the laser beam, this is the cylindrical lens, then there is a converging lens which basically creates the laser sheet. Okay, so you can also see it with concave lens, which is negative focal length lenses. So there is a parallel beam. It basically opens up the beam using a convex lens of constant, of certain width, constant. So you can see that this is, for example, diverging width. This is width. So this is routinely used in measurement. So typically this is like an Nd:YAG laser, which is basically expanded. First it is routed or basically deflected, guided. Then you use this arrangement of cylindrical or concave lenses, and then use a convex lens, basically open up and form a sheet. And the flow is laden with tracer particles. And as these tracer particles passes through the laser sheet, it will actually, scatter light, and that is what you monitor with the camera. If you monitor with a single camera, we get a 2D PIV field. If you do it with two cameras looking at an angle, this is what gives rise to the three-dimensional PIV or the vector field. Okay, and then of course there is image processing and other things that you do. So, but this is light sheet optics, which basically consists of nothing but a cylindrical lens or a concave lens, and you use a convex lens basically create the sheet of constant width or diverging. Okay, more we will talk about these sheets and how the sheets are actually, sheets are made. That is a topic in itself. We talked a little bit about this we'll talk a little bit about this in the LDV and more about it in PIV. Okay, so now that we have done that, you have seen that some optics fundamentals we have covered. We have covered visualization, hardware, cameras, and lens systems. And now in the next lecture onwards, we will do light propagation and scattering. So just a quick recap. We did spherical aberration, which is basically the off-axis parallel rays, but which are off axis, which basically gets focused at different points, which are away from the axis. That gets focused at different points. As a result of that, you get both longitudinal as well as transverse spherical aberration. This leads to image blurring, essentially. You can also have astigmatism, which is basically when the object lies away from the focal optical axis. As a result of that, the meridional plane rays and the sagittal plane rays, which are shown over here, they actually focus at different points. The focal lengths of these planes are actually different. As a result of that, you have astigmatism. And then we talked about chromatic aberration, which is nothing but the colors because of the dependence of refractive index on the wavelength. Okay, and this leads to differential focusing of the different colors of light, and this also can have lateral as well axial chromatic aberration. And then we talked a little bit about the different types of cameras that are there. Okay, high resolution cameras to low medium resolution camera. And then we talked about the signal to noise, and where we said that when the signal is small, if the noise is also small, signal to noise ratio is small, that's some cameras, you will have the noise and the signal of comparable values probably. Okay, so the signal to noise ratio is not that great, but it can improve if you, even for low signals, if your signal to noise ratio is pretty high. Then we talked about the long distance microscope, the telecentric lens, which is important because it wants to make the objects appear of the same size. Okay, so this is used in the industry, even in machine vision and stuff like that. And you also use laser light sheet optics, where you have to create a sheet from the light using a combination of cylindrical and positive focal length lenses. In the next lecture, we are going to talk about light propagation, scattering.